Good afternoon, friend. In last lecture, we have discussed about Hooke's law, types of modulus of elasticity, that is Young's modulus, bulk modulus, and modulus of rigidity. And we have completed the Young's modulus and bulk modulus. In this lecture, we have learned about modulus of rigidity. What is modulus of rigidity? It is defined as the ratio of tangential stress of shearing strain. Let a tangential force F be applied to the upper face of the cube. In this diagram, this A, B, C, D is the cube. We apply a force to the upper surface of the cube, then upper face of the cube. Then this upper face, that is of side L, is displaced to another position, that is A dash, B dash. Okay, and this is shown in figure. Let layers parallel to the upper face of the cube displace along F along a distance small l with respect to lower fixed face, with a point A shifting to A dash, point B shifting to B dash. So what is shearing strain? That is A dash divided by AD, where A dash is the change in original length. Okay, and AD is the original length, that is D. Okay, so shearing strain is equal to A dash upon AD, that is small l divided by L. It is a shearing strain, that is tan phi. Phi is the angle between AD and A dash. Okay, so as a phi is very small, so we consider tan phi is equal to phi. Therefore, modulus of rigidity, which is represented as eta. So modulus of rigidity eta is equal to, that is what? That is stress upon strain. Here is a shearing strain. So what is stress? That is force upon area. So modulus of rigidity force upon area is equal to divided by shearing strain. So we get final equation, that is F is equal to A into phi. It is also known as coefficient of transverse elasticity. Okay, so again I repeated this modulus of rigidity. First, what is the definition of modulus of rigidity? It is defined as the ratio of tangential stress to shearing strain. Okay, modulus of rigidity is defined as the ratio of tangential stress to shearing strain. So for this, we consider a cube of side L, A, B, C, D, and we apply a force to the upper surface of the cube. Okay, when we apply a force, then the upper surface is displaced along the direction of force. So the point of upper surface, that is A, is displaced to A dash, point B is displaced to B dash. So therefore shearing strain, that is equals to small l upon capital L, and it is called as tan phi. Okay, it is nothing but tan phi. We have a question, how tan phi is here. So we know that is in right angle triangle, that is tan tan of any angle is equal to, that is the opposite side upon adjacent side. So we get a tan phi is equal to opposite side, what? That is small l, and adjacent side is L. So this is L upon small l upon capital L. It is the tan phi. Okay, so this is occurs between, that is the right angle rule. Okay, so as phi is small, tan phi is equal to phi. Therefore modulus of rigidity can be written as eta is equal to stress upon shearing strain. So shearing stress is the force upon area upon phi is equal to F upon A phi. It is also known as coefficient of transverse elasticity. Okay, now we see the Poisson's ratio. So when a wire Okay. So now we see the Poisson's ratio. When a wire is stretched, its length increases. When a wire is stretched, its length is increased, but its diameters are reduces or decreases. This the linear strain, that is the strain along the direction applied to load or length of wire, is always attended by the lateral strain or strain along the lateral or perpendicular to the direction of applied load. Okay. So in this diagram, this is the suppose the length of a wire, so which is stretched by so the length is increases by small dl, and the what is but the radius of this is decreases by small dr. Okay, original length is r, so it is decreases by dr. Okay, so the Poisson's ratio sigma is defined as the ratio of lateral strain to the longitudinal strain. What is Poisson's ratio? It is defined as the lateral strain to the longitudinal strain. So sigma is equal to lateral strain divided by longitudinal strain. So if F be a force applied at a free end of wire of length L and radius R, then dl is the small change in length, and d and dr and dr be the corresponding change in radius of wire. So longitudinal strain is equal to change in length upon original length, and lateral strain is equal to change in radius upon original radius. So here negative sign shows that the radius of the wire is decreases. Okay, so therefore what is the Poisson's ratio? Sigma is equal to what? That is lateral strain upon longitudinal strain. So we put the value of longitudinal strain and lateral strain. So lateral strain is equal to minus dr upon r divided by, that is longitudinal strain, dl upon l. So we get that is this term l from denominator goes to numerator, and in upper term small r, the value of r is going to denominator. So minus l upon r into dr into dl. If alpha and beta be the longitudinal strain per unit stress and lateral strain per unit stress, then sigma is equal to beta upon alpha. Okay, suppose we consider the longitudinal strain is denoted by beta, that longitudinal strain per unit stress we define as beta, and lateral strain per unit stress then it is given by alpha. So we get that is Poisson's ratio is equal to beta upon alpha. So Poisson's ratio is a dimensionless quantity and its values lies between 0.5 and minus 1. Okay, you understand? Okay, I repeat it once again. So first of all, what is Poisson's ratio? So we know about definition of Poisson's ratio. Poisson's ratio is nothing but it is defined as the ratio of lateral strain to the longitudinal strain. Okay, so therefore Poisson's ratio sigma is equal to Poisson's stress upon sigma is equal to lateral strain upon longitudinal strain. Okay, if suppose we consider a wire, so what we can get, so we stretch a wire by applying force. Okay, so if be a force applied at a free end of wire of length L and radius R, so then what happened, the change in length is occur and reduce in radius. Okay, so dl and dr be the corresponding change in length and radius corresponding change in radius of wire respectively. So longitudinal strain is nothing but the small change in length upon original length, that is dl upon l, and lateral strain is equal to change in original radius upon original radius. Okay, so this is decrease in radius, so minus dr upon r. So therefore sigma is equal to minus dr upon r into dl upon l. So we get minus l upon r into dr upon dl. So if alpha and beta longitudinal strain per unit stress and lateral stress per unit stress, then sigma is equal to beta upon alpha. Hence Poisson's ratio is a dimensionless quantity and its value lies between 0.5 to -1. Okay, thank you.